Hi YouTube, my name's Hiro. I'm a 5-year experienced mechatronic engineer, and I'm here today to talk about my Lego Quadruped robot. So a little bit about me. I've got 5 years in the industry. I've been involved in car servicing and control systems from prior uni. Some control systems were built for Arduino projects, such as this one and other ones. I've also been involved in industrial automation. I've had a position doing electronic testing and PCB design, and most lately I've been doing electrical design in the subsea space. So this quadruped robot was the reason I became an engineer. It's a big shout out to Paul Wilcox and Rodney Parsons of SciTech. They were the mentors that led me to build this robot. And today I'll be talking about the way it works and also the function block diagram, like what the hardware, what it looks like as a system. So let's run through the hardware of the robot. So here we've got the battery. See that in yellow? That battery goes through a switch. That switch then goes to what's called an ultimate battery eliminator circuit, which is a UBEC. That UBEC is situated just under the Arduino there. That UBEC is what converts 7.4 volts to 5 volts, which is then used for the control system and the shield, which powers the motors. So the control system there is the Arduino, and then you've got the shield on top, the servo shield, that drives the motors. You can see all these wires coming off for the motors. Lastly, we've got the XB there, and that allows wireless communication with the controller. So if we have a look at the controller, it's the controller here. We've got 2 inlets here for different options for power. We could have USB power, or we could have a 9-volt DC jack. That's the Arduino on the bottom. Then inside we've got the midway, we have the XB shield. That's its own little shield there. Lastly, we've got the joystick shield on the top. So this comprises the controller. So if we run through what these systems look like as a function block diagram, on the left here we've got the robot, got the LiPo battery feeding 7.4 volts into the UBEC. That UBEC then converts that 7.4 volts into 5 volts, which is then used by the Arduino, the Zigbee shield, the servo shield. And then the servo shield, as you saw, had all these cables going to the motors, M1 through to M8. That robot's communicating with the controller via the 2.4 gigahertz frequency. And this here is the function block diagram of the controller. It's quite simple. We've got a 9-volt battery or a USB. We've got an Arduino, Zigbee shield, and a joystick shield. So in robotics, degrees of freedom is described the maneuverability of an actuator. So if we have many degrees of freedom, that means the arm can go very, very many different angles. For this robot, that's 2 degrees of freedom. You've got this motor here, and you've got this motor here. Reason for this choice of configuration for the legs is because 3 degree of freedom leg design was quite popular in the market, and we wanted to try something different. So this design is quite challenging to steer because, as you can imagine, we don't have the third motor, which means that you can change how these legs are oriented. We can only go back and forth with the leg. We can't go in an arc-like direction, allowing for kind of steering. In this diagram, the way it could work if we had a 3rd degree of freedom is this chassis here would be broken off. We'd have another motor attached here, and this would allow this to pivot about this point. And those legs would move in an arc-like motion, should extend the range of motion and also allow for turning. So how does it work? Each leg has 2 motors, and these 2 motors are controlled simultaneously to move it through a scooping motion. You can see here we start at the retractor position, ready for a stride. And we'd go through, and we're trying to get as low as possible and also as straight as possible as it returns. Get to the end of the stride, and then we would return to the very start. And the way that would happen is we'd start off in a set position. We'd then enter a for loop, which might have if statements nested in it, and these if statements would control how much motor movement there is relative between the legs. And then at the very end of the stride, once it's reached the end of the stride, we'll have a fixed position command again to go back to home. How does it work as a system? It's quite something else. So we have this method of control for the legs. If we're talking about maybe a cheetah or a 4-legged animal, if you really slow them down and pay attention to how they're walking, all 4 legs are doing different things different times. they're staggered with respect to each other. And by that I mean you have one leg that starts at stride, and maybe midway through that stride, the next leg has started. And midway through that stride, maybe this first leg cuts and stops, and it's able to restart its stride, so it'd be back in a retracted position. And it restarts, but then every single leg is staggered with respect to the other leg. And then you reach a point like here, and this is the point which is where it's completed one walk cycle, one like effective gait. It's gone through all of the walk movements, and we've already started again with the first leg here, which has restarted its walking cycle. The reason there's two lines here for each of these four is because that represents 2 motors per leg. So we've got 4 legs, 2 motors for each leg. So 2 by 4, that's 8. And that's what the actual control system uses. It uses an array of 8 continuous numbers in real time, which will feed to these motors and control the walking gait. This is you could call this a static control system for the walking. It's not able to tolerate a huge incline or a huge decline for the robot, but there is enough there is enough balance in the robot that it can tolerate a little bit, and it can walk on different surfaces. It can walk on the carpet. It walks poorly on like a bench top because it's slippery. Has these little rubber grippers to help. So this walking cycle is how it's able to control walking straight. But when we want to actually have control for steering, we have to change the walking cycle in real time. And the way that's done is one of these 2 front motors is disabled partially for its walking movement during these periods. When the command is sent to turn left or turn right, one of these motors does less work, and that means it's staggered. It's not working as much, and because it isn't working as much on one side, the robot will tend to overtake it from the other side, which is working harder to walk. That's a wrap, guys. Thanks for checking out the video. Any questions or comments, please comment below.